Electrostatics or static electricity you probably have experienced in your everyday life, whether it's getting an electric shock when you reach for a metal door handle or just getting staticky hair when you pull a sweater over your head. The first person to actually document this phenomenon was probably a Greek by the name of Thales, around 600 years BC. And the Greeks used amber, which is fossilized tree resin, for creating jewelry. We still use it today. And the Greek word for amber is electron, which is where we get the word for electricity and for the particle, the electron. And Thales noticed that these amber bits of jewelry, when they rubbed against a woolen shirt or a piece of hair or fur, would build up a static charge. And they would attract other little bits of dust, hair, fiber, and hopefully you've done this experiment already, but if you take a rubber rod or a glass rod and you can build up a static charge on that object and attract little bits of particles. So you're building up a static charge on that object, and that's static electricity. And that occurs when we transfer charge from one object to the other. So rubbing the glass with silk causes a transfer of charge. Now, in an atom, we know that the charge is produced by the electrons and the protons. Electrons are negatively charged and protons are positively charged. And interestingly enough, they have the same magnitude of charge, which we call the elementary charge E, 1.6 times 10 to the negative 19 coulombs. The unit for electric charge is an uppercase C, which is a coulomb. So the electron and the proton each have the same magnitude of charge, but they're opposite in sign. Protons obviously are positively charged, electrons negatively charged. So if an atom has an equal number of protons and electrons, it will have no charge. It'll be neutral. Now obviously the protons themselves are stuck in the nucleus of the atom and we can't get them out. If we tried to get a proton out of the atom, we'd have to split the nucleus apart and it would stop being an atom of that element, whatever element we're looking at. But the electrons, because the electrons are orbiting around the nucleus, if we give those electrons enough energy, we can extract them out of the atom and transfer them from one atom to the next. So it's that transfer of electrons that creates a charge. Now the symbol for charge is Q, and the amount of charge that gets transferred, well, we just have to look at the number of electrons that have been transferred and multiply it by the charge of an electron. So either we're gaining electrons and creating a negative charge, or we're losing electrons and creating a positive charge, because what's left behind are a bunch of atoms that have more protons than electrons, so they have a positive charge. Okay, so the important thing, like I said, is that the transfer of electrons is what causes that static charge. We're either transferring electrons to or from an object. Okay, so suppose we have two different charges. Let's suppose this one is positive and this one is negative. Okay. Now, positive and negative charges, as long as they're an opposite charge, they will attract each other. So there will be a force experienced by each charge of attraction towards the other one. Okay? And if they're two of the same charges, in this case they're both positive, these two charges will both repel each other. Okay, so opposites attract, like charges repel each other. And it's the same if they're both negative charges. So these two negative charges also experience a force pushing each other apart. Okay. Now, the person who came up with the relationship that gives us this force is a French physicist by the name of Coulomb. We call this Coulomb's law. That's where we get the unit for electric charge from Coulomb. So Coulomb's law is take a constant K, which is Coulomb's constant, 9.0 times 10 to the 9 Newton meters squared per coulomb squared. That's not the speed of light squared, that's charge. Then multiply the two charges and divide by the distance between them. Okay, so again, r is the separation between the two objects. And what you should notice is that this equation looks very similar to Newton's universal law of gravity, right? Same form, g m1 m2 over r squared. So again, this type of relationship is a 1 over r squared proportionality, right? So F is proportional to 1 over r squared, meaning that if you looked at a graph of force and distance, the graph would get progressively smaller, exponentially smaller as you approach 0, and it would go towards 0. Okay, so it's a 1 over r squared relationship. The other thing to note is that since it's a force, there's obviously a direction, but the direction is often going to be easier to determine by looking at the sign of the charges in your diagram. So I don't need to rely on the mathematics to tell me the direction of the force here. I know that these two charges repel each other. All I want to know is the magnitude. So quite often I tell students, don't bother putting in the sign of the charge. Okay, so leave the sign of the charge out of the equation. Okay. You're just looking for the magnitude. Rely on your vector diagram to determine the direction of the force. Okay. Because it gets quite complicated, especially when you have both positive and negative charges, you would end up with a negative force. That negative does not necessarily mean that it's in the negative direction. The negative there would indicate that it's an attractive force. Here with two negative charges, we'd obviously end up with a positive force because we'd have negative times negative. That positive is not indicating positive direction, it's indicating a repulsion. Yes, the force on this charge is in the positive direction, but the force on this charge is in the negative direction. So it tends to get a little bit confusing when you start including the sign and getting positives and negatives. It's best to look at your vector diagram to determine the direction of the force. And it's really important that you get the direction from your vector diagram when you have more than two charges to deal with. So for example, here I have three different charges, and I have two negative ones and one positive charge. And if I wanted to know the magnitude and direction of the force on this charge here, I first need to draw the vector diagram. And this charge will have two different forces acting on it. These two charges repel each other. So there is one force acting in this direction due to the repulsion between these two charges. But these two charges attract each other, so there is a second force in this direction. So the net force on this charge, if I add these two vectors as I normally would, the net force would be somewhere in this direction. Okay. So that's why it's important that you find the magnitude of each individual force using Coulomb's law and the direction using your vector diagram. Right? Same thing for F2. You're going to find the magnitude of each side of this vector diagram using Coulomb's law, and then use your vector analysis to find the net force and the direction of the net force. Okay. And you're not going to put in negative for the charge because you're going to use your vector diagram to find the direction. Okay. Now there's lots of good examples of using Coulomb's law in the textbook, so you can work through those. And if you have any questions about Coulomb's law, make sure you come ask me in class.